Hi, thank you for connecting to watch the video on the independence of association bias and empirical fairness in language models. This is work done with my colleague Anna and my supervisor Anders Søgaard at the University of Copenhagen. We as researchers have been prompting pre-trained language models to probe them for strong associations between protected attributes, such as gender, and value-loaded terms, such as job title. The problem is that many of these works suggest an intimate connection between bias and fairness, or simply the distinction between the two is not clear. In this work, we aim to provide conceptual clarity by distinguishing between association biases and empirical fairness, and we will show that the two can be, in fact, independent. How are we going to do that? We will start by providing definition of these two concepts, and then we will jump into a three-way analysis to show that this concept can be, in fact, orthogonal, or in other words, that you can modify bias without affecting fairness, or the other way around. Let's start talking about association bias, which is the most common conceptualization of representational bias in natural language processing. When we talk about association bias, we will be referring to systematic differences in how phrases or words referring to demographic groups are encoded. Traditional metrics that have been used to measure or quantify this bias is cosine similarity between the word embeddings. On the other side of the wall, we have empirical fairness, which is defined as performance disparity. We will say that a model is fair if it achieves equal performance across groups as measured by de facto standard metrics. In the literature, we can find numerous fairness definitions which account for different scenarios. Therefore, we can also find many different metrics proposed to quantify such fairness. In the end, we can classify all these metrics in three different classes depending on whether they account for recall, precision, or balancing the two. In this paper, we will be working with precision-based metrics, and we will account for the min-max difference, for the min-max gap in performance between the worst of and the best groups. We can start now with our thought experiment. Let's say that we have 4 groups of users labeled as North, East, West, and South, and we have a predefined vocabulary, which is these 7 words that the people from these groups use to talk about sentiment. The first 5 words, including those associated with each group, are used for talking about negative sentiment, while good is for positive and neutral is not conveying any sentiment. Let's say that the members of these groups use these words with the following probabilities for talking about sentiment. We can see here 4 representational biases, which is, for example, the association of each group with the negative sentiment. We can also see that 25% of the time, for example, the group North will be using Eastern to convey negative sentiment. If we have sufficient data, we can train a simple model like naive Bayes to perform sentiment classification. The model will induce the maximum likelihood estimate given a negative sentiment, for example, as we show in this table. We can see that the model reproduce the representational biases found in the data. Now, say we employ an existing debiasing approach and manage to debias the model with respect to its representation for the first group, the group North, which means to account for the word Northern. This amount to equal the following probabilities given any class of sentiment. And looking at the green box on the left, we can see that this will hurt performance on data from the group South, as it will increase the empirical risk of this subpopulation. But what is more surprising is that this will not help us on classifying the data from the group North, because it wasn't using the word Northern in this context to begin with. What we want to show here is that removing biases in how terms referring to a group are represented, in this case Northern, only improve performance on data from this group, in this case North, if these members use such in-group terms more frequently or in different ways than other groups. In the absence of this assumption, as we just saw in the example, bias and fairness are orthogonal. We refer to this assumption as the in-group affinity assumption, and we will be referring to it in the remaining of the presentation. If we can look now into a practice exercise when we train actual models evaluating on actual data designed to prove the models for bias and fairness. We will take gender as our case study, and we will measure bias with the following 3 metrics, which are template-based and were recently proposed in the literature. Empirical fairness, building on top of work from Zhang et al., which designed a fill-in-the-gap task and asked annotators to complete the missing words, and at the same time collected various demographic information. We will be only using gender. As I mentioned before, this is our case study. The metrics used here to account for fairness are the min-max difference in precision at 1 and the difference in mean reciprocal rank between male and female groups. We can visualize here an example of the results for one of the bias metrics employed and the 2 fairness metrics, precision at 1 on top and MRR at the bottom. On the y-axis, we have bias, and on the x-axis, we have fairness performance. Ideally, we would want all the models to lay in the 4th quadrant, which would mean that they have low bias and high fairness, but we can see that this is not often the case. Red points are the clear counterexamples to such a negative correlation between bias and fairness. Finally, we would like to provide some examples retrieved from social science literature that show how we tend to talk more about others than about ourselves, supporting that the in-group affinity assumption doesn't hold in reality, and this is clearly connected with the thought experiment that we saw at the beginning. But there is one exception for which the in-group affinity assumption holds, and these are slur terms. We'll leave this as a cliffhanger, so if you are interested, you are very welcome to go to the paper and read about it. Finally, our takeaway message here is that association bias and empirical fairness are not synonyms, and we should not conflate both terms. Association bias and fairness are not causally connected, and in fact, we've shown that the 2 can be independent. Thank you for listening. Hope to see you all in the conference.